Hello, my name is Dian Chen, and it's my absolute honor to present you our winner solution for the 2021 Kala Autonomous Driving Challenge. This is joint work with my PhD advisor, Professor Philip Crombie at UT Austin. Autonomous driving has been one of the most anticipated technologies ever since the advent of modern-day AI. To navigate a vehicle safely from point A to point B, it is a consensus that an autonomous driving system needs to solve the task of perception, planning, and control. However, even after decades of exploration, we have still yet to see autonomous vehicles deployed at scale. In fact, we have been promised by multiple different companies that we'll have fully autonomous vehicles in 5 years for the last 10 years. Deciding whether we will have autonomous vehicles by one of the companies above is out of the scope of this talk, but the question instead we want to ask is, what has been preventing us from having full autonomous vehicles driving on our roads? What are the biggest obstacles? Well, the answer, as everybody says, lies in the long tail of driving scenarios. So similar to the driving stack, the long tail also comes from both perception and the action end. For perception, there are exciting research fields such as open vocabulary object detection that specifically aim to tackle this challenge. But this talk, however, will instead only focus on the long tail on the behavior and action in the autonomous driving. So what does it mean for a problem to be long tail? For autonomous driving, it means that the majority of our driving logs consist of only normal driving scenarios of the ego vehicle. However, safety-critical and accident-prone scenarios happen rarely in the dataset, and some may never even happen twice. Moreover, such scenarios are extremely diverse. There are probably hundreds of driving scenarios that are less complicated compared to the picture shown here in the right, but equally difficult compared to the picture shown here in the right. The long-tail distribution of driving scenarios poses great challenges to both classical and learning-based motion planning methods. And the question you want to ask is, how do we tame the long tail of the driving scenarios? One direction is to collect a large and diverse dataset to train learning-based motion planner. However, an expensive data collecting ego is unlikely to give us more diverse driving data, and this is because test drivers in these vehicles usually drive very conservatively in order to avoid damaging these expensive vehicles with expensive onboard sensors. Another direction is to train agent in closed-loop simulation with handcrafted or learned difficult driving scenarios. While this direction enables infinite amount of data and can train agents on safety-critical scenarios that we don't normally see in driving logs, it eventually will face the challenge of sim-to-real transfer. Moreover, simulating all agents on the road in a realistic manner while covering all the modes is actually an extremely difficult task. The third direction is to come up with a better representation for the downstream motion planning task. And when we talk about long tail distribution, what we're actually talking about is the long tail of a joint distribution of the inputs and labels. This long tailness can be caused either by the long tail distribution of inputs or the long tail conditional distribution of labels with respect to the inputs. With a fixed dataset, there's nothing we can really do about the inputs, but we can actually come up with a more generalizable intermediate representation that makes the conditional distribution less long tail. However, in this work, we actually propose an orthogonal direction to tame the long tail and can actually be combined with all the directions shown above, which is to, instead of training from only the ego vehicle, actually train on all vehicles. And why do we do this? Our method is actually motivated by one very simple observation. We observe that although most of us have not experienced traffic accidents ourselves, we have at least observed a couple of accidents in our driving careers. And the same thing applies for safety-critical scenarios for the data collecting vehicle. Although the ego vehicle might not have experienced safety-critical situations itself, its driving logs likely contain interesting or accident-prone scenarios that are experienced by other vehicles. Therefore, training on how other vehicles move can help the model see more and diverse data. At inference time, knowing how other vehicles might move can also enable more complex reasoning in the downstream control. While this seems natural at first glance, it's actually not as straightforward to implement. The main challenge is that, unlike the Eagle vehicle, which we have direct access to its onboard sensor and control commands, other vehicles poses a partial observability challenge. First, unlike the Eagle vehicle, other vehicles expose no control or high-level commands. This means that in order to train from their motion traces, one must infer or recover their high-level goals or commands. And more generally, or more importantly, other vehicles do not have accessible sensor readings. This means that the learning system has to infer other vehicles' surrounding state from the Eagle sensor readings alone. Directly handling the two partial observability problem is difficult because the system is tasked to learn from both perception and both partially observed perception inputs and partially observed motion levels. To address the issue and make the problem easier, we use a privileged distillation approach inspired by our previous work, learning by cheating, where we handle the partial observability on perception and action separately. And to put it more formally, in our work learning from our vehicles, we built a joint perception, prediction, and planning stack. We train the system using data from all nearby vehicles using a staged privileged distillation approach. We start with our motion planning system. We first train a privileged motion planning model. In this stage, we use traces from all nearby vehicles to train the models. This model takes as input privileged ground truth state of the simulator that are represented as rasterized bird-eye view image, where each channel represents occupancy of a certain class of traffic elements, such as roads or vehicles. A neural network then takes as input the crop region of the bird-eye view image and predicts the future position of the vehicles. We use multi-branch architecture following the prior works. To handle the partial observability of motion commands of other vehicles, we infer their high-level commands using future waypoints, and we train the network branch that correspond to the inferred high-level command. Note that in this privileged motion training stage, we only handle the partial observability of motion labels, and we ignore perception. Next, we discuss how we handle the partial observability of perception inputs. In parallel with the privileged motion models, we train a perception backbone using mapping and object detection under supervision. And this stage serves two purposes. First, it helps train a viewpoint invariant intermediate representation. And by forcing the representation to produce road and detection maps, we hope to make the intermediate feature representation indistinguishable in the eyes of a motion planner. And secondly, these detection results actually can also predict poses of other vehicles at test time, which can use to crop features at test time to predict their multimodal future trends, trajectories. That's enabling us to have more complex reasoning in the controller. Finally, we use a privileged distillation to stitch up these two models. In particular, we train a full sensory modal motion model that uses the pre-trained perception backbone and predicts multimodal future trajectories conditioned on the high-level command for all vehicles or all nearby vehicles in the scene. And we do this by distilling from the privileged motion models that are learned in stage 1. Similar to our prior work learning by cheating and work on Rails, we use multi-branch supervision to obtain a denser supervisory signal. Here are two visualization examples of our final model's prediction. Mapping, detection, prediction, and planning results are overlaid in the above visualization. Note that how our model predicts consistent multimodal motion plan for all detected vehicles in the scene. It also predicts reasonable road topologies, suggesting that the features have successfully captured road information. Our method, learning from all vehicles, currently ranks first on the CARLA leaderboard and has won the 2021 CARLA Challenge. It outperforms prior methods by a wide margin 10 points higher than in driving score, and even more in the root completion rate. And thank you for your attention. We'll release our archive and code in about a month, and please stay tuned for the release. Thank you very much.